And then the second video covers some more of that Chapter 16 special topics, and then this video is covering all of Chapter 17 and Chapter 18, the beginning of Chapter 18 at least. So let's just jump right in. So the first thing that we're talking about in Chapter 17 is the acidity of carboxylic acids. So as the name implies, that these functional groups are acidic species. So you know, if you place this molecule in some sort of basic media like water, or you know, anything with a pKa over 5, so like sodium amide would be a sufficient base like NaNH2, or you know, maybe some sort of source of hydride like NaH, you know, these are all sufficient pKa's, have over 5, that can, you know, deprotonate that hydrogen on the carboxylic acid. So mechanistically, you know, if you were to draw in this Lewis structure of water, we could expect that a lone pair would grab a hydrogen off of there and push that on top. So the end product would be something like this. And I just wanted to make a note that this molecule, this anion, is called a carboxylate, if you see that. So carboxylate anion. Okay, and that carboxylate anion is actually resonance stabilized. So you can see, and I'll draw the resonance arrows in purple, I can push these lone pairs in and kick that up, and the alternative resonance structure would be something like that. All right, so it's resonance stabilized, which means that, you know, these products at the end are more favorable than their starting materials, so we would, you know, have the equilibrium go to completion, and this is actually a favorable reaction. Okay, so just note that if you see something like that on the exam, you know, with a base that is sufficient with their pKa values, we can deprotonate that carboxylic acid and, you know, form the carboxylate anion. All right, so what are the two ways that we can actually prepare carboxylic acids? Well, the first one, you know, is review. So oxidation of a primary alcohol using a strong oxidizing agent. So in this case, I'm showing an example of this primary alcohol under sodium dichromate conditions. You could have used potassium dichromate or Jones's reagent, and that's just going to take this this alcohol rather, all the way to the carboxylic acid. So it looks like this. All right, there's nothing more to it, that's simple. All right, so I just want to count my carbons here just to make sure you see that we have one carbon here and we have one carbon here on that substituent. All right, so over here, the second way, which is new to this chapter, is Grignard nucleophilic attack. So I can take an alkyl halide like this molecule, turn it into the Grignard, and then do nucleophilic attack with carbon dioxide to form a carboxylate anion. And then, you know, the final step is just that acidic workup to protonate that carboxylate anion. So let's just show the product of step 1. The product of step 1 would be the Grignard reagent, so it's 3 carbons and MgBr. And then I'll just draw in carbon dioxide here in its Lewis structure, so it's a linear molecule. And those sigma bond electron density is going to attack that carbon, push these pi electrons up to form a molecule that looks like this. 1, 2, 3, 4. So this is our carboxylate anion, and all that hydrochloric acid and water is doing is serving as a proton source for that carboxylate anion to become fully protonated. So the end product is this carboxylic acid. Okay, so what I do want to point out to you guys is, let's count the carbons in the starting material, and let's count the carbons in the ending material. So 1, 2, 3, and then if I go back over here, it's actually 1, 2, 3, 4. So the difference is that when I do the oxidation of primary alcohols, I'm going to retain the same number of carbons that I had in my starting material, but when I do the Grignard nucleophilic attack with carbon dioxide, I'm actually adding one additional carbon, and that's evident right here in that carbon dioxide step. So we're actually adding a fourth carbon to this chain, so that's just something to be cognizant of in synthesis. If you see in your starting material that you're adding one carbon in the ending material, you must have gone through some sort of Grignard nucleophilic attack with carbon dioxide. All right, so reductions of carboxylic acids. So I made an announcement, and I'm going to make another announcement again in an email just so you guys understand. I did make an error where I said that a hydrogen with platinum, palladium, or nickel is sufficient enough to reduce carboxylic acids to alcohols, and that is not true. Only LAH is. So, and LAH is also only carbonyl specific, so the only thing that LAH can reduce is carboxylic acids, aldehydes, and ketones. It won't touch any alkenes. So I'll just know that that carboxylic acid is what's going to be reduced to a primary alcohol. So my carbon count is 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And we're going to have that primary alcohol at that position, and we're not touching that alkene. All right, so again, you might see lithium aluminum hydride written as LAH, just shorthand notation, and that's going to reduce, like I said, the carboxylic acid, the aldehyde, and the ketone. So if I were to draw in the carbon 1, 2, 3, 4, 5 carbon count, 1, 2, 3, 4, 5, we'd have that primary alcohol over here from the carboxylic acid. We would have a secondary alcohol over here, which is racemic at that position, so you need to draw wedge dash configuration. And then at this position, you would have another primary alcohol, and that is also another chiral center. All right, so just make sure that you would have 4 stereoisomers for this one, 4 stereoisomers. All right, so that is a lithium aluminum hydride metal reduction for carboxylic acids. All right, so one of the most useful reactions in this chapter is called Fischer esterification. So basically it is adding in this ethanol molecule into this benzoic acid under acidic conditions, and fostered by the removal of water will bring this equilibrium to completion. So mechanistically we can rationalize that. We'll just redraw starting material over here. That ethanol and nitric acid is going to be this protonated version of ethanol, and we are going to activate that carbonyl to make it electrophilic enough for nucleophilic attack from this ethanol molecule. So we are going to form this molecule. So now that carbonyl is sufficiently electrophilic for that plain ethanol molecule to just do attack. So we can draw that mechanistic arrow into here, and we just formed this molecule. So what we want to do is we'll take this molecule of ethanol again, and we'll remove a hydrogen from that ester, I guess, group that we just formed, well, the ether group. And we are going to form this. And that. So what we want to do is convert one of these hydroxyl groups into a good leaving group. So we can just take that protonated version of ethanol and then give a proton to one of those hydroxyl groups. It doesn't matter which one in this case. All right, and then the product of that step would be something that looks like this. And the driving force of this reaction to completion is, one of these lone pairs from the hydroxyl group resonating down, and we'll kick that off as a good leaving group. So then our end product of that, we're one step away after this. All right, and our one step is just taking a molecule of ethanol and removing that hydrogen from that carbonyl. So we just formed an ester functional group. All right, so that is our molecule, that's our end product. So, just following this mechanism, it's the same thing that we've seen over and over again. We have to activate that carbonyl because we're reacting with a weak nucleophile. So activating that carbonyl with an acid will make it a strong electrophile. So then once that electrophile is sufficient enough, we can do nucleophilic attack with the alcohol. That comes in. We want to take a proton off of that ether functional group, give it to one of the hydroxyl groups to make it a good leaving group. The driving force is resonating one of those pairs of lone pairs on the oxygen down to kick off water as a good leaving group, and then the final step is just removing that proton from the carbonyl to regenerate our catalyst. All right. So here's another example of Fischer esterification, but it's intramolecular. So I did want to point this out. So if you want to count your atoms in this chain, it's 1, 2, 3, 4, 5. So we're expecting a 5-carbon ring, or just a 5-atom ring. 1, 2, 3, 4, 5. And then if I were to number it, 1, 2, 3, 4, 5. At position 2, we're going to have an ethyl group. And at position 3, 4, 5, so at position 5, we're going to have that carbonyl group, all right? And that carbonyl group next to that, oxygen is an ester, but more specifically, we're going to call it a lactone. And if we wanted to be more specific, and have proper stereochemistry with this ethyl group, what we decided is we're going to assign RNS configuration for this hydroxyl group, and that needs to be retained, for the ethyl group in the end product. So we're going to assign RNS for this molecule. Priority number 1 would be this group. Priority number 2 would be this group. Priority number 3 would be this group. And 4 is on a dash, so that we're in the right orientation. So this is definitely going to be an R configuration. So we need R configuration in our end product. So if I were to assign priorities here, we know that this is going to be number 1 to the left, number 2 is going to be towards the right, and then number 3 is going to be the actual ethyl group. So if I were to trace that priority, it's going to be S. So that means that we need to have this ethyl group on a dash. And that's correct. At least proper stereochem. Alright? Alright guys, so the next reaction we're going to consider is acid chloride synthesis with thionyl chloride. So just about a little bit of review with what we've seen thionyl chloride before, but we've seen it with primary alcohols or just any alcohol, and we can use SOCl2, and we used to see PYR abbreviated there, and what would happen is that we would convert that alcohol into the haloalkane. So the same thing now can happen with carboxylic acids with the OH functional group, and we can turn them into something that looks like this, and that's the acid chloride. Alright, so let's just show the mechanism. It's the same thing like we saw back in Orgo 1, but let's just go through it again. So if I redraw that starting material down here, we can draw in, thionyl chloride's Lewis structure, and we can rationalize that these lone pairs on the carbonyl will attack that sulfur and force those pi electrons up. So we just formed a product that looks like this. Alright, and then the next mechanistic step is we need to generate some sort of source of chloride, to do nucleophilic attack in the carbonyl. So I can rationalize that these lone pairs will resonate down to kick off a molecule, an atom of chloride. So the product of that would be something that looks like this. And this is our chloride that we just generated. And now that chloride can do nucleophilic attack into the carbonyl and push those pi electrons up. So that's going to form our tetrahedral intermediate. So we're going to have, O minus, actually not O minus, I'm sorry, O with the SOCl. We still have that hydroxyl group, and now we have a chloride. So the next, driving force of this reaction, which we've seen, is we have these lone pairs on the hydroxyl group, come in and force off that whole molecule as a leaving group, but, we still need a source of chloride, so we're going to kick this molecule off. So this looks a little bit funky with all the mechanistic arrows, but recall that we have the hydroxyl group lone pairs resonating in, which kicks off that really good leaving group, and one of our products is SO2 and Cl-. So we regenerate another source of chloride. So the product of this step is going to be something that looks like this, with a chlorine. I know, kind of funky how I drew that. And we did generate SO2. Oops, let me zoom out here. We did generate SO2 at this position, and we did generate a chloride at that point. All right? So we're just one step away. So what we can do is we can use that chloride that we just generated in that last step, and we can remove that hydrogen to form the acid chloride. So yeah, this mechanism is a little bit funky, so drawing that end product, we would expect something like that acid chloride. All right, let's just look at the mechanism overall one more time. So what's happening is that the carbonyl lone pair electrons are attacking thionyl chloride, which forces those pi electrons on the oxygen up, but we want to generate a source of chloride from that crazy intermediate. So what we can do is resonate those lone pair electrons down, kicking off a source of chloride. That chloride can now be available to do nucleophilic attack, making that tetrahedral intermediate. And we said that the driving force of this reaction is those pi electrons on, those lone pair electrons on the oxygen resonating in and kicking off that leaving group to form SO2 and a source of chloride. And then that chloride can be used to do an acid-base reaction with that H on the carbonyl group to form your acid chloride. All right, so the final reaction, it's not really a reaction, but it's called decarboxylation. So if we have something called a beta-keto acid, the carboxylic acid will actually leave the molecule as carbon dioxide gas. So if we were to assign alpha and beta positions, this is the alpha position and that's the beta position. As long as I have a beta carbonyl group, so it doesn't have to be a keto, it could be an aldehyde as well, that we can facilitate the removal of that carboxylic acid. So the mechanistic arrows are something like this. So all I'm doing here, if this may not be clear, is rotating around this bond so that we're in, this conformation. And it's going to make sense in a second. So what happens is that these pi electrons in the carbonyl will grab that hydrogen. Those bonded electrons will now go here to form carbon dioxide, but you exceed the octet at this carbon, so now you need to swivel over and form that. All right? So the steps of after that problem would be something that looks like this. Okay, so that's our final product. So if we see our carbon count in here, it's 1, 2, 3, 4. So it's 1, 2, oops. 1, 2, 3, 4. That methyl group still came for the ride, and then this whole carboxylic acid group left as carbon dioxide gas. All right. So that's a really easy question. Just make sure that you have that carbonyl group in the right position, which is the beta position relative to the carboxylic acid. All right, so that's the end of chapter 17. So let's just do the first two reactions of chapter 18, and they are the carboxylic acid derivatives, and we're just going to talk about the hydrolysis of these two derivatives. So the first one is hydrolysis of acid chlorides. So over here. So what's happening is that we can have this source of water molecule add in to form a carboxylic acid instead of the acid chloride. So we have seen, at this point that we can go from carboxylic acid to acid chloride by reacting with thionyl chloride. But if I had an acid chloride and I wanted to go back to a carboxylic acid, I could use a molecule of water to do so. So the way that we can do this is, if I just drew the Lewis structure over here for water, that lone pair on the oxygen will add in like that, push the pair of pi electrons up. So the next step of that would be something that looks like this. And what we want to do is now we have this choice of leaving group ability. So we can have this water leave as a leaving group, or we can have this chloride leave as a leaving group, and they're both good leaving groups. But we want the chloride to leave, so we need to make the water a worse leaving group. So the way that we can do that is just take another equivalent of water, and that water is going to deprotonate this water substituent to form just a hydroxide functional group. Oops. So the molecule will look something like this. And what can happen now is that these lone pairs on that alkoxide anion can resonate down, and when they resonate down, they kick off that source of chloride, not this hydroxide. So that doesn't get kicked off now because we just made it a worse leaving group by removing one of the protons in that last step. So the product of this step would be something that looks like this. All right, so that is the product of this step. I'm sorry, chloride left. It's carboxylic acid. All right, and then we just generated a source of chloride. So mechanistically, that makes sense. We didn't really touch any stereochemistry there, so you can keep that wedge configuration of that methyl group. And that's it. That's the schematic of it. So the whole concept of the hydrolysis reaction is that once you do nucleophilic attack with water, you have two good leaving groups. The chloride is a good leaving group. Likewise, that water is a good leaving group. So what we want to do is have chloride leave, so we need to make water the worst leaving group, and then by resonating those alkoxide lone pair electrons into the to form a carbonyl, we can click off the chloride exclusively and not the hydroxyl group. It's the same thing for the hydrolysis of acid anhydrides. So you could actually do this either way. You could have decided to add water into, this carbonyl, or you could have decided to put water into this carbonyl. Your choice. You're still going to get the same product, and the mechanism would be the same. So what you could do is draw the mechanism like this. So if I had my molecule of water, mechanistically you would expect those lone pairs going in here. So if I were to just zoom out, Okay, so right now at this position we have two good leaving groups. We have water, and then this whole ester functional group. Those are two very stable leaving groups. So we want to convert the water into a bad leaving group and just, maintain that ester as a good leaving group. So the way that we can do that is we can take another equivalent of water, like we've been doing, and just remove a proton of that water and put those electrons back on. So we would get a product that looks like this. All right, and then we know we have these lone pairs on the alkoxide anion that come down and kick off that functional group. So we just formed, benzoic acid, and then we formed this alkoxide anion. So then, since we have hydronium in solution, that final step would just be to protonate that alkoxide anion. So this is the first reaction that we have seen where we actually generated two major products. So if you saw this on the exam, you would be expected to show both this structure and this structure, all right? And that makes sense. So you can basically just visualize this molecule and splice out that position, and you could have, actually not that position, sorry. You could have drawn a line through that oxygen and rationalized that the left side is benzoic acid and then the right side is just another carboxylic acid, and then you would just predict the products in that sort of fashion. And that's the end of your exam material. So let me know if you have any questions, and good luck.